We all know that this colloquium is in the memory of late Professor R. Ananthakrishnan, who was ex-director and honorary fellow of IITM Pune. So our today's speaker, let me introduce about today's speaker. Our today's speaker is Professor Ralf Toumi, who is a co-director of Grantham Institute, Climate Change and Environment, Imperial College London, UK. Professor Toumi was awarded PhD from University of Cambridge. Initially, he worked as a lecturer in the chemistry department in the Cambridge and fellow in the physical chemistry at Christ College. Then in 1994, he moved to the physics department at Imperial College as a lecturer, became professor of atmospheric physics in 2004, and was head of the space and atmospheric physics group from 2014 to 2020. Since 2020, he has been a co-director of Grantham Institute, Climate Change and Environment. Regarding his awards and honors, there are many. I'll just list a few. What he received: Philip Leham Prize for Scholars of Outstanding Distinction in 2002, a Merit Award by Imperial College for Outstanding Achievement in Research in year 2004, a Royal Society Industry Fellowship for the duration 2006 to 2010, a NERC Knowledge Exchange Fellowship in adaptation of energy sector. Then Professor Ralf Toumi has co-authored and reviewed many international reports such as WMO Ozone Assessment, SPARC and IPCC reports. He has published many papers. He has served as ESA Mission Advisory and the European Commission Climate Service Roadmap Groups. He is an advisor to WMO Asia Pacific Typhoon Collaborative Research Center on the board for Japan Typhoon Drop Zone Day program. He has co-investigator in the UK Center for Greening Finance and Investment. Over his career, his research has covered a wide range of topics in climate science, atmospheric chemistry, and physics. He has supervised about 34 PhD students, and he leads the largest research group in the tropical cyclone in Europe. With this brief introduction, I invite Professor Ralf to deliver talk.
Thank you. Thank you for coming, and thank you for having me. It's always a great pleasure to come here. I was trying to remember the first time I came here. It was with one of my PhD students. I think it was 1990, and I was saying when I was coming here, at that point, I think they were just starting to build a computer here somewhere. But every office we went to visit, many scientists, I think they've long retired by now, but every office, they had a room, a picture, sorry. It was a hand-drawn picture, I think, mostly, of the all-Indian monsoon rainfall. So there was a time series, and it was almost like every room I went to was like a stock market index. The all-India rainfall was like the key figure, and I had a great time coming here, and I've come back several times. So today I want to talk to you about some recent work we did on tropical cyclone and its dependence on pressure tendency. And I'm aware that most of you are not into tropical cyclones, so I'm going to do this very gently. So the important aspects of cyclone structure, tropical cyclone structure, is that obviously it's a rotating flow. We all know that. You actually have an inflow in the boundary layer, which is largely frictional driven. Then you have these what we call these rain bands, which include ascent as well as descent. You have a central very strong, so this is what we call the eye wall here. So this is the strongest winds. So it's this region here, the wind speed here, which is actually used for characterizing the cyclone. So that's what's characterized by the wind speed. But I think it's quite important to recognize, and that's relevant to this talk, that when people talk about the wind speed, it is really just one measurement, the maximum wind speed somewhere here along the eye wall, right? So if you imagine the radius of an eye wall might be, I don't know, 50 kilometers, you're really talking about a diameter of several hundreds of kilometers, and somewhere in there, along here, for 1 minute or 3 minutes, you have a sustained wind speed, and that becomes the number, right? And forevermore in the data record, it becomes a very strong tropical cyclone or a category 3, 4, 5, whatever. Of course, nobody ever measures this. This is very important to remember. None of this is measured. So this estimation is largely based on what's going on in the cloud field. And some observations made in the US where they actually made some drops on and they looked at the pattern of the cyclone. So, but where there are no in situ observations like the North Indian Ocean, this alleged wind speed is purely driven by what the cloud pattern is. So there's a technique called the Dvorak technique, which is what people use to do that. And that involves some skill. In other words, error. And this is really one of the big problems. Our data set is really not great for this whole problem. So I mentioned the cloud cover. So the situation then you have inflowing cyclonic, and then you have this outflowing anticyclonic pattern, and then you have this very extensive cloud deck. And when the cyclones are very strong, you have this sort of descending motion here, which then creates the eye, the very famous eye of the tropical cyclone. So this is the basic structure. And what about the most fundamental theory? The most fundamental theory is something that was posed by Kerry Emanuels, and his theory takes the analogy of the Carnot heat engine, and this is really the prevailing paradigm. So Meda and I do tropical cyclone research. It's very rare that you come across a paper which doesn't sort of refer to this paper by Kerry Emanuels, which is basically based on this theory. So I think it's important just to go through it because it's sort of like the baseline for this entire field, really. I would say. So the full description I showed you was a sort of 3-dimensional structure. So this is now a very simplified 2-dimensional structure. So it basically imagines that you go through a series of cycles like you would with the heat engine. So leg 1, and in many ways this is a really, really really important part, is that you have the air parcel, as I said, was sort of flowing into the cyclone. As it's doing that, it's taking up heat from the ocean. So this becomes the ultimate source that drives the whole part of the cyclone energy, because it's really the input of the surface heat fluxes in this leg. But the key point is that this leg here, this one, is meant to be an isothermal expansion. So the idea is that while it's taking the heat, the temperature actually stays more or less the same. But as you're putting the heat in, there's also the low pressure, so actually there's an expansion as well. So this leg here is an isothermal expansion. So you're expanding the column, so expanding the parcel, if you like, the pressure drops, but the temperature remains the same. And this is then the most important leg. Then you have the second leg. So this, of course, now you're beginning the ascent in the eye wall. So this becomes an adiabatic expansion. So you're expanding and rising, and then this cooling then by the expansion is partially offset by latent heat release. And I say partially because it is not perfect, but it is nearly balanced. But there is sufficient buoyancy to keep driving the leg 2. Then you exit, leg 2 here, you exit and you go on to leg 3, which is the outflow. So at this point, you're losing heat by radiation cooling to space. And of course, then this is an isothermal compression. So at this point, you end up with going back to the ambient pressure, if you like, at that level. But again, you assume that the temperature is the same as you go across the leg. So there's an adiabatic warming, which because, of course, now you're compressing, and that is offset by the cooling. So you have the radiative cooling, and then you've got the heat input here, and then you've got a little bit of subsidence because of the cooling, I guess, and then you complete the leg by adiabatic compression. But actually, this completion of this leg could be a long way away, and in fact, this whole cycle could take a very long time because it's not something that can be completed probably in the whole time scale of a tropical cyclone, like 3-4 days. In the Indian Ocean, probably less than that. So the whole cycle probably takes much longer than that. But as a concept, you've got all the different processes involved, which are really fundamental to the energetics of the cyclone. And this then leads to this very famous idea of maximum potential intensity by Kerry Emanuel. And basically, there's a conservation of energy. Work in equals work out. The work done, in this case, it's friction. So this is the interaction at the surface during the work. So we find it as a drag coefficient, and then becomes the cubed of the wind speed. And the work in, you have heating because you have this heat flux exchange. So that's the enthalpy exchange. So that's the leg one, if you like. But you also have some heating because of this friction. So you have a small frictional dissipation term as well. So that's your energy input generated by the cyclone. And this is the Carnot efficiency. This is reflecting that the sea surface temperature and the outer temperature, the outflow temperature, are different. And then this becomes sort of an efficiency of the engine. Because the energy of the classic the thermodynamic engine is really to do with the efficiency, is really just the difference between the heat, the cold, and the warm reservoir. In this case, the warm reservoir is the ocean, the cold reservoir is the upper atmosphere. So you have an efficiency, and then you put everything together and rearrange it, and then you end up with this key term here. This is the potential intensity, the wind speed now. And then that just becomes a combination of constants. So this is the enthalpy flux coefficient, the drag coefficient. So these are constants, which are not very well known under cyclone conditions, but anyway, they are the drag coefficients we normally take, the efficiency terms, and then just the difference in the heat flux, the contrast of the heat flux. So this gives us an idea of the maximum potential intensity. So that's quite a powerful constraint, because it tells us, well, how strong can a cyclone possibly get? And this is, of course, easy to calculate. I mean, these numbers I can get hold of. I can use reanalysis. I can use a climate model. I can do a lot of things. It's not a difficult calculation. It's an analytic solution which everybody loves, everybody can work with. So it's extremely widely used. Some advantages and disadvantages, like with any theory. So I've just sort of outlined some of the advantages. So one of the big advantages is based on physics. So it's based on the heat engine, thermodynamics, nothing more natural than that. It is simple. You know, I can write that equation on the back of an envelope. It's analytic. That means I can apply it in lots of circumstances, and it provides an upper limit, theoretical upper limit. The weaknesses of it. Actually, if you look at the actual intensity, we call this a lifetime maximum intensity, and you compare it to the potential intensity, and you plot a probability distribution, you have actually what's known as a uniform distribution. Now, I don't know if anybody knows here what a uniform distribution is, but if you're dealing with any form of statistics, it is the worst probability distribution. Because unlike if you imagine a normal distribution, which is we like, you know, it has a mean, I have a confidence around the mean, there's some, you know, central value I'm expecting, that's my normal distribution. In fact, most distributions have some sort of expectation of what the characteristic value is. So that's a good place to start. The uniform distribution says that any value is equally likely. So you think, well, that's not great, really, right? So I can predict the upper limit, but if I then wanted to use the upper limit as a predictor of the actual intensity, I'm completely lost. It can be any number. So that's a bit depressing, because it means I cannot use this analytic model in an operational sense. I cannot really use it for forecasting purposes. I can use it to inform myself, to understand some physics, but it has no practical utility in terms of being a predictor because of this uniform distribution. So clearly, there's a lot of things going on where the upper limit is set by the thermodynamics, but the real value is really, really dependent on lots and lots of factors. So that's the first problem. It's a weak constraint. It is also an equilibrium theory. It is really a theory where the cyclone is in a completely mature stage, and I'm very close to the engine. I'm operating at full strength, which is why I said you should look at the lifetime maximum intensity maybe as a measure of this. So it's not a tendency. It does not explain to you how do I get from A to B to this completely mature stage. There's no information there at all. It's going straight to the thermodynamics. So in chemistry, there's this term called thermodynamics, and then you have the kinetics, or in dynamics, thermodynamics, right? So the dynamics is the evolution, the thermodynamics is the constraint. So there's the constraint, but no tendency. The other thing that's missing, which is the talk really I'm trying to get to, as you will see from the equations, there's nothing here about size. There's nothing on size. This theory has no concept of size or what it means or how it's important or anything like that. So what about the size? What about the size of the cyclone? So the size of the cyclone is important for at least practical reasons, because if you look at the damage a cyclone does, intensity, of course, is important. But of course, if you have the eye wall and you damage, a building or anything like that, when the building is destroyed, it's destroyed. After a while, it doesn't really matter. It doesn't really matter if the wind speed goes up another 50%. But the size means how many buildings can you destroy? And so if at that point, you can have a lot of damage. So the damage itself actually is very closely related to the size, the total damage. So a cyclone that is weak, but very large, so Sandy is probably the most famous case in the North Atlantic, a cyclone that maybe covers half of the east coast of the United States. Of course, the damage is absolutely colossal. But at the time, it was maybe a category 1, barely what we consider a hurricane, but it was vast. So size is really, really important. It's not just the intensity. But of course, traditionally, the forecasts and in public conception, it is all about this intensity value, which, as I explained to you, is one value in the 300-kilometer diameter for 5-10 minutes. The size, there's no 5 or 10 minutes, right? That is really a beast that is going to affect a lot of people. So that's really what constrains the damage. So size is important. And so what we try to do is to examine the problem from a point of pressure. So one of the advantages of pressure, it doesn't have this problem the wind speed has. So the wind speed is just 1 point, but the pressure is the total mass of the column. It is also a value that is not easy, is easily to measure in principle, but of course over the ocean we don't know it either. But it's also a variable which is going to be quite stable, because of course the wind speed at 10 meters, there's a lot of turbulence going on and fluctuations. But the column mass is hard to manipulate. So when the minimum pressure is something, it's not going to change over the next minute, 10 minutes, whatever. It's quite a stable measure. And therefore, from a physics point of view, it's an attractive measure. And therefore, we can maybe approach the problem not from a conservation of energy, which is what I was explaining before. This is the classic Emanuel approach, conservation of energy. So what we're doing here is we're doing it from the conservation of mass. So I'm going to treat a column simply as a cylindrical column. So the column has a sort of mass. It has a certain height. It has a radial mass flow in and out. It has a gradient, so I have a central pressure and I have a pressure in the outer, for example, this could be the eye wall. So I have a central pressure, I have the eye wall, and I have this distance r, outflow, height, and I have the column mass. So if I wanted to consider the mass of the cylinder, the tendency of the mass, I would simply consider the circumference, and then I would integrate the density, and so I should have probably done it this way around. Well, no. I'll stick with this one. So if I wanted to work out the tendency of the mass, so the rate of change the mass changes, I would consider the density integrated over height. So that gives me the actual mass. And then I need to integrate the mass outflow or inflow, but let's assume it's an outflow, integrated over the height. So this is the rate of outflow over this height. So that gives me the rate of mass leaving my column. The pressure, the average pressure inside this radius is simply the mass over the area. So that's just a standard usual definition of pressure. And I can calculate the pressure also from the hydrostatic just by integrating the density. So the pressure at R, so this is not the center, but at R, or at any radius R, is just the integral of that density. I can then also calculate the outflow, and I need to consider that the outflow itself should also be pressure weighted. So the mass outflow will vary with height. And because the density changes with height, I should really weight the VR by the density of the column. So this is sort of a pressure weighted outflow. So basically, I'm simply saying something very basic, very elementary, that to understand the rate of change in mass in the column, I need to understand the rate of change of mass going in or out. Very simple mass conservation. I don't need to know anything about temperature in here or anything like that, or anything about wind speed in here. It's just I have a mass. If I want to change the mass or the pressure, the only way I can, by conservation of mass, I can change the pressure is I need to put mass in. That will be inflow. If I want to change the pressure, I need to move mass out. I don't need to do anything. Don't need to know anything else. Of course, the tricky bit is what is this VR? That's the harder problem. But fundamentally, from a physics point of view, pressure tendency is just the change in mass. I need to put mass in or mass out. We can say, well, therefore, the pressure tendency, the average pressure in my column, is simply the change in mass. And therefore, I can then equate the rate of change of the pressure to the pressure at the outer eye wall, for example, where this is the pressure at R, the outflow at the barrier, at the outer cylinder, and that will be at some distance R. So basically, the mass flux leaving my cylinder is what I'm doing here. So this is the pressure and the outflow value of the R. So this gives me a pressure tendency. And what you can see here already appearing is a dependence on R. And that essentially comes from the fact that I'm considering the outflow would be across the entire diameter. So I've outflow anywhere across the whole diameter of my vortex. But the pressure or the mass is really determined by the area. And the ratio of those two then leaves me with this R term here. So what I'm indirectly getting now is actually a tendency, the pressure tendency, which depends inversely on the radius. So it depends on the size of my cylinder, my vortex, if you like. And this is purely comes out of it's a basic geometric argument. So I have a pressure tendency, which depends on the radius R. Of course, the pressure tendency also depends on what pressure you start from. And obviously, it depends on the outflow or inflow. So if I have more inflowing mass, obviously the tendency is going to be larger and so forth. So I basically have three factors then that determine my pressure tendency: the pressure at the outer eye, the pressure at R, the radius R, and the outflow or inflow. The observations, we don't actually have the observations at wherever I want to draw the circle, right? So I'm not even specifying that this is necessarily the eye wall. I'm saying, let's suppose it's the eye wall, but it could be any radius from the center. But the value that I do have from observations, and ultimately I want to test this theory, is only the center. So I have the minimum pressure, the central minimum pressure. So I also need to somehow get back to that value, because that's the observed value. So if I want to test my theory, I'm going to have to go back to that measurable, or at least reported value. And so actually what we find is that we can examine the pressure at R max in a model, for example, in a basic theory as well, simple pressure rating, and I can relate it to the central pressure. And the pressure at R max, so this is the average pressure, so this is the mean pressure as a function of R max. I can compare that to the central pressure, or the pressure at R max, I can compare that to the central pressure. And there would be some sort of scaling. So the mean pressure scales in some way to the central pressure, and this would be the scale parameter. So I don't know a priori what that is. but I can then rearrange my equation. So rather than doing the average pressure in the column, I can now rearrange it and do what I can actually get data for, which is the tendency at the central pressure. So the central pressure tendency. And I so retain many of the values. So it depends on the central pressure tendency, central pressure itself. This is now the outflow integrated with height. So it's still my outflow. And I now have an R max, which is another variable I observe. And I've got this gamma, and this gamma is the ratio of my parameters, which is the pressure at R max and then the average pressure up to R max. And basically, this gamma is roughly equal to 1. So you can basically just treat this as 1, and you can basically simplify the whole problem to this. So this then becomes what we derive as the central pressure tendency. So it simply says the rate of change of the central pressure is proportional to the central pressure itself, the outflow rate of the column, and the radius of maximum wind. So now these I have reported value. So I have an archive, it's called the IB tracks, which is recorded for all cyclones all over the world. The quality varies depending on where you are, because sometimes I have aircraft observations. In many places like Indian Ocean, I don't. So I have data for this. I don't know this. This is the outflow. So this number here includes all the problems which we are normally trying to understand when we do tropical cyclone modeling. We're trying to understand, oh, well, what's the frictional inflow? What's the convection doing? Where's the outflow? What is the outflow rate at the top? What about mixing entrainment for the clouds and the environment? All of the complicated stuff we do with numerical modeling. All of that, all of the detailed physics, if you like, everything I need to know to really make a predictions about tropical cyclone, all the physics I am hiding here. I'm putting it in this value here. Because what I'm saying to you is that if I want to understand the pressure only, all of this physics, all of this complication I'm doing, in the end, if it's changing the pressure, it has managed to take mass out or put mass in. And basically, the rate at which you're doing that is captured in this parameter chi. So I'm hiding all the physics, but of course, if you're the central pressure, you don't care how you got your mass or you lose your mass, but this is how it varies. So I need to know it clearly. I need to know this value to get the tendency. But crucially, I have now separated out two other parameters which are going to be important for this tendency. So everybody understood that this value is going to be important for this. Not so clearly understood is how does this value depend on the initial pressure and on the size, crucially. And it's the size that's the new insight here. So that's something which is a new insight. This is a trivial insight, and in fact, this is the focus of all the work in tropical cyclone intensity forecast. How can we get this number better? But this then makes a very clear prediction. It says my tendency, my observed pressure change, should vary with the inverse of the radius. Or more precisely, because it's PC dPc here, it's the log. The log of the pressure tendency should vary inversely with Rmax. This is the prediction of the theory. So if we assume a constant inflow and outflow over a time step, and so this is why we say, this is a tendency. So tendency is really an infinitesimal small change, right? So over some change, it could be 30 minutes, an hour, something reasonable, I'm going to assume that the outflow or inflow is constant. But that tendency could be anything. I mean, it could be a second, or it could be anything you wanted. So then it allows me to do this integration. In principle, the log of the pressure at some time t over some time t will depend over Rmax. So basically, the evolution of pressure should be an exponential. And this then, the Rmax or x naught over Rmax is actually the half-life or the doubling time if you were doing pressure increases, so that we are weakening. But for a pressure decrease, which is intensification, it's basically the half-life. So the half-life of a pressure tendency should simply be proportional to the radius of maximum wind and this value here. And we'll just assume that for this time, over this time step t, the inflow-outflow is constant. So just to re-emphasize, I'm doing the tendency, right? So this is not a prediction over 3 days or something, right? Because of course, during that time, I'm not assuming that the inflow or outflow is going to be constant. It's going to fluctuate because of all the physics complications I mentioned to you. But if I start zooming in on smaller time steps, then it's maybe quite reasonable to assume that this is a constant. In fact, it's something we can check with the data. So that's one of the things we've done. But in essence, we have a very simple exponential dependence of the pressure with time. So what about the data? So what we did here was we examined all intensifying cases. And the first thing we did was we picked the North Atlantic. So initially we did it globally because, of course, we are globalists. We are in London, so we don't have any hurricanes. So for us, they're all the same. But then the referees are probably in America. So they say, no, we have the best data in the world. You need to do it for North Atlantic because we have the aircraft, which is fair enough. They have the aircraft. So he said, okay, do the North Atlantic, which is the best size data. So what we did here was we looked at all the 6-hourly changes. And then we did the ratio of the pressure. We did a log. And we bin it by the size. So at least since the last 20 years or so, there have also been reported of size. So this is, we'll have errors as well, but at least it's been reported. So we have the observed size. We have the pressure change over some fixed time period, 6 hours in this case. And so we can plot it. So we have 1,700 observations. So in our theory, log PP naught over 1 over R max should be a straight line. So the correlation coefficient is reasonable. It's not fantastic. It's 0.41, highly significant. The slope actually tells me the mean outflow. So this, assuming that I have the same outflow in all cases, then that would be your mean grade. Of course, you can see the scatter here, right? Lots of these are gray points of the different points. But of course, the actual outflow, in my theory, I can still predict this number and this number perfectly if I know the outflow, right? So the outflow will vary hugely. So the outflow can vary by factors of 10. And of course, then I can use my equation. I just have a different flow and a ratio. So the equation will always hold. But because the outflow will vary so much that you end up with a lot of scatter. So that's why the R is that. But anyway, even assuming there is a mean outflow of 0.29, you end up with this answer. Interestingly, if you then look at the strongest changes, so this is the 75th percentile. So when the pressure change is the largest, the correlation becomes actually much better. And if you go to the even stronger outflows, you end up with these outflows of 3.1. So you can see the range of outflows are quite increase as you go to more and more extreme pressure drops, which is encouraging. So it's saying when the pressure changes are quite large, this theory seems to work quite well. When the pressure changes are small, it's actually quite noisy. There's a lot of different things going on. Now, it's worth bearing in mind here that the pressure, again, is not observed, right? It's estimated based on the cloud pattern. The size is also uncertain. So our theory is our theory. The observations are not perfect. So, but that's what it shows you. So I think it's at least consistent, sure, let's put it like this, for the intensifying case. But of course, the tendency doesn't care. If I have outflow, then the pressure drops. I can have inflow, the pressure goes up. The equation is the same as conservation. So I can also do the weakening cases. So the pressure now is going up, and I can see the same thing. Basically, correlation is a little bit worse. We think partly this could also be with the problem of the observation. So one of the problems what happens with during a week when the cyclone is strengthening, very often you have an eye forming, right? So, and the cloud patterns are very clear. But when the cyclone is beginning to collapse, it may well be collapsing at the surface, but there's a sort of memory in the upper level cloud field. And also the upper level cloud field is beginning to distort the eye, and it's becoming increasingly difficult to estimate what is really going on at the surface. So the decay phase is actually very, very hard in this satellite technique to characterize. So that's also well known. So I suspect the errors on the pressure changes are even larger, and also on the seismometer. Probably not so much on the seismometer, but the tendency also. So what you often find when it is decaying, there's a bit of a lag. So they report the same value for several time steps. Then the cloud field change, and they go down. So when I do my finite pressure change, the reported value would maybe be the same, but I would say actually it's continuing to go down, and so there's a lot of error in these 6-hourly changes, because I don't really have real 6-hourly changes. I have 6-hour guesses essentially, but the behavior is the same. The correlation is still highly significant. And then, of course, we had to do global because we want to do everything global. And basically, the answer is the same. The correlation is it's a little bit worse, but it's more or less the same. The behavior is the same. If you look at the more extreme pressure drops, the percentiles of this slope here, then you end up much stronger outflows. And if you did the 99th percentile, you end up with this. So we did the 99th percentile in the global case and in the upper one, because if you can see here, it looks like we can maybe recover what I started at the introduction was this upper limit, right? So we had an upper limit for the intensity. And what I'm trying to explore here is, have we got an upper limit for the intensification rate? I mean, that might be useful as well. Right? So how strong can a cyclone strengthen or indeed weaken? Because basically all the data points are beyond this line, the 99th percentile. So that might be of value, because it says whatever you're doing now from a forecasting point of view, these are the limits. But the limits depend on the size. So 1 over R max obviously means that these are quite strong, quite small cyclones. So this is an interesting potential application. So I said it's a tendency, so it really depends on your time step. So how does it do if you change the time step? So we had 6-hourly, 12, 18, and 24, even 38. So basically the correlation was even better if you went to 12 hours, but I showed you 6 hours. And then it gets worse with time, as it should. And this is the correlation is actually for the weakening is actually good, best for 18 hours. And this again could be because actually the observations, by 18 hours, I could be quite confident that I've had the weakening. I don't want the satellite confusion about the cloud image, so that it might reflect that. This increase here might also be reflected by the fact that the 12-hour intensification. So, the agencies are maybe they're hedging their bets, they're waiting a little bit. By 12 hours later, you can be quite sure that it's gone up or down. So again, the apparent correlation may really just reflect the observation. But basically, as you would expect, the outflow cannot be constant as you move in time, so the correlation tends to drop. And the mean outflow rate is interesting here. Actually, so the slopes change with our time step as well. So the effective outflow decreases for larger t. So it's interesting. So I have, for 6 hours, I have a sort of characteristic outflow or inflow, which is actually quite similar, interestingly enough. So the inflow and outflow rates, according to our theory, looks quite similar. Then if you take bigger time step, the slopes get shallower and shallower. In other words, the rate of increase is in the 12-hour and 18 and 24-hour is not as dramatic as you might get at 6 hour. And that sort of makes sense, right? Because whatever 6-hour changes you've got, you've moved it, you can't sustain that for 12, 28 hours. Because actually in the real world, because of the physics works, you have a bit of inflow, but then you might have a bit of net outflow. It's going to be quite noisy. And so when you average longer 1 day ahead, you're going to end up with lots of sequences of inflow, outflows, inflows, outflows. It might be a net outflow or a net inflow, but it's not going to be as dramatic as the 6-hour changes. So basically it just drops very nicely. So that also makes sense. And then this was the 99th percentile. And here you can see that we have a simple prediction. So the maximum intensification rate is proportional to the central pressure and the radius. So this is something you can use operationally. You can say, well, okay, it cannot get worse than this. If I know my Rmax and I know my central pressure, this is it. For weakening, similar number, actually, 0.9, same dependence. So the interesting thing here is that smaller, the lower Rmax, and weaker, so this would be a higher pressure, right? Because it's a negative for the tendency. So a higher pressure cyclones have the most rapid changes. So this is quite interesting because it says actually a weak, small storm are the ones you need to worry about. They are the ones, according to this equation, that are most likely to rapidly intensify. And in fact, that's what we see. If we look at the observations, when people look at the wind speeds, they have already shown, or there's been some just statistical correlations that actually the rapidly intensifying cases, which is the most challenging part of forecasting, are often associated with smaller cyclones. And the theory so far, before this, because they're dealing with it from an energetics point of view, is they argue that the smaller cyclones are more inertially stable. So the inertial stability is sort of the extent to which the vortex can resist radial motion. And so a smaller vortex is what we call is more inertially stable. So when the heating happens, the theory goes, the heating is confined inside the vortex more tightly because it's inertially stable. The heat cannot leave the cyclone. That heating creates a pressure drop through hydrostatic approximation, and then you end up with a pressure drop, and then you end up with a stronger cyclone. So the theory before this was really around inertial stability, a dynamical explanation, but not a prediction. It was just simply saying, well, that sort of makes sense. Smaller cyclones should intensify more. But there was no theory in the sense of a prediction, but there was an understanding that's how it should work. So on this mass conservation rule, it's very simple. If your cone is small, your cylinder is small, your outflow is constant, a smaller cylinder is going to evacuate more quickly. It's simple geometry. There's no need to invoke inertial stability dynamics. It's just geometry. A smaller cyclone at the same outflow rate will intensify more quickly. And the dependence, it's not that it's proportional, it's a clear dependence on the log of the pressure change is 1/Rmax. So that's one thing. So smaller storms will intensify more quickly. So when you do the operational prediction, you have to include size. If you got the size, you're not going to do the tendency. So this is actually a real problem because no, we don't do the size very well at all. And so if we don't do the size very well, if you get all the physics right? And I said this was the physics, this was the outflow, this is the convection, wrong tendency, you're going to get the wrong wind speeds. You cannot escape the geometry. And so the size has to be modeled correctly. This is a real problem because if you do a forecasting problem and you have a problem with the size and you have a problem with the initial value, the initial value problem we all know, if your initial pressure is wrong, your tendency is going to be wrong. This is also saying, well, actually, if your size is wrong, you have a double problem. If it continues to be wrong, you have a triple problem. So this grows exponentially, this problem. It grows exponentially with your initial size problem, which you need to adjust, and your initial value problem. The second thing about the weaker storms. So it also means that weaker storms have the potential to intensify more strongly because, like I said, a higher pressure will give you a higher tendency. So again, we sort of see that the maximum rapid intensification is typically in weakish storms, not the weakest, but it's in weakish storms. So it's not the weakest, probably because they're also quite large. So at the genesis point, we have quite a large, circulation. It's quite weak. So that works against you here. But then when the system is getting a little bit stronger, so the Rmax is beginning to pull in, the pressure is still reasonably high, bang, you're in the rapid intensification phase. At the final end, right, your cyclone is now getting, your cyclone is getting really, really strong. You already, the pressure is already dropped. This is working against you. Your outflow, inflow are going to be much weaker because the mass available is much less. But also, very importantly, at this point, the Rmax tends to be small. So at that point, there's not much to be gained anymore. And that's what this seems to say. I'm here, so I want to tell you about the North Indian Ocean. So yesterday I was at NCWRF, and I said, okay, so what's the latest then on what's going on in tropical cyclone forecasting in India? So they showed me this work by Kumar, very recent, Kumar and colleagues, NCWRF, and started with the good news. This is the error in the position. So this is the old version, new version, and great, much more improvement. You can see here another way of showing the forecast hours. So the red is the new model. So it looks fantastic, right? So the 5-day forecast is basically like the 2-day, maybe something. There used to be the 2-day. So that's great. So you walk away, everything's done. Not quite, never quite done. The error, or the total error, is actually made up of, so I should have said yes, so the total error here is basically what it was, 48 hours. But what they then did, they broke it down into two different errors. So this error can be decomposed into two different errors. So there's the along track error. This is basically, if you're following the track, are you jumping ahead? Are you lagging behind? This is one of your errors. So that's the error that is improved. So the improvement is consistent across all timescales. So the rate at which the model is forecasting the cyclone to move along whatever the track is, great improvement. This is the cross-track error. So this is the departure. So this is are you going left and right from the track essentially? Are you veering off? Are you getting the direction right? So this is equally important because if you look at the value of the errors, it's about 100. It's about 100. So this is an equal source of the error. And this has not improved. The 5-day forecast, if anything, it seems to have got worse. So there's nothing going on here. So even in the track, which is really the thing that people get, say, yeah, we're doing track really well, which is what this plot would suggest. If you decompose it, there is still a problem. So the veering, the left and right veering, is not been solved at all. And we were sort of scratching our heads why that is. I don't know why that is. He doesn't know why that is, but it's a fact. So there's work to be done. It could be, my hypothesis is we know that the steering wins as the large-scale flow. So we all know the models have been getting better. They should do better assimilation, better physics, whatever. So the steering winds, which are driving the cyclone, is really a measure of the large-scale circulation. So it's a test of the large-scale circulation, which is basically pushing the cyclone at the right speed. And it's definitely doing that better and better. But this cross-track might be more complicated because actually maybe what's going on here is that the cross-track isn't just simply the steering, the large-scale steering. It could be an interaction, particularly with the wind shear of the cyclone itself with the environment. And this could be also influencing the track. And we know that the models, all models, not just this model, all models really have a problem with intensity. They just don't do intensity very well at all. So if your cyclone intensity is wrong, it could be that combines with the interaction of the environment to give you a wrong cross-track error. It's a hypothesis, I don't know. But the real problem is here, which is the intensity forecast. Right? This is not good. If you look at the differences here, so yeah, it looks like the new version has a lower, basically mostly below the blue. So on that basis, it looks okay. But the shape is shocking. The shape is just fundamentally wrong. It's just telling you there is something completely wrong going on, because you should never have a 5-day error which is the same as a 1-day error. If you've got a model that tells you a 5-day error is the same as a 1-day error, you are probably just predicting the same number randomly. And so you're not making any forecast at all. You're probably taking a climatology, and you're just saying it's that, and sometimes it's high, sometimes it's low. But to have a shape like this, I mean, it should be an alarm bell. I mean, it's like you cannot have this. The error should behave like this. The error should increase with forecast time. So of course there are some issues. Many cyclones don't last the full 5 days, although it doesn't stop the error from going up. So the sample size is not great. I think it shows you here that most of the counts maybe peak at 2 days because they make landfall. So you're sort of running out of room here for the long tail. But even then, there's no sign of any error growth. So So I think there is a challenge here about forecasting tropical cyclones. I wouldn't be surprised, actually, if this also extends to the monsoon depressions. Because the monsoon depressions are really just another version of the cyclone. So people say, oh, the cyclone season is nothing to do with the monsoon, it's pre-monsoon and post-monsoon. But actually, there is from the view of depressions, the Indian monsoon depression cycle, seasonal cycle, is actually the global tropical cyclone cycle. So the monsoon depression cycle is really part of the global cyclone cycle. It's just that because of the shear, and Meda explained the position of the ITCZ, cyclones don't have a chance to develop. So they collapse at landfall, maybe they form even over land. The shear reduces their intensity. So you basically have a depression cycle, which is actually a very classical peak for the global cyclone cycle. But because of the shear and the position, it sort of hits the intensity, and you have this you eating out the heart of the peak of the cycle. And you end up what looks like 2 tropical cyclone cycles, pre-monsoon, post-monsoon. But in reality, you have one cycle. You have one physical problem, which is the depressions, the monsoon depressions. And so if the monsoon itself shifts, you're probably eating into the cyclone cycle, if it shifts in time, etc. So I think and it'll be very interesting to see whether this problem here isn't actually the same problem in the monsoon depressions. So part of my mission here for the next 2 days is to convince the monsoon mission to reconsider their lack of interest in tropical cyclones, to consider tropical cyclone as an extension of the monsoon depression problem, to consider the interaction between the end of the monsoon and the beginning of the monsoon and the tropical cyclones. And I think there's much to be done in this space. And I think it's a very important topic. Conclusions. So we produced an exponential model of TC, which we tested, has an inverse size dependence on weakening rates. It identifies a size constraint therefore this is a constraint for climate models as well, right? You cannot do cyclones if you don't do the size. I mean, that's basically what this is saying. You cannot do it. It's inherent by mass conservation. So that's a real constraint on weather forecasting. So we published the paper, and we have a project. So there's an app called DreamLab. You can download it. You can run a cyclone model while you charge your phone. So you can have a look at that if you want. It's called DreamLab. So you can download that off the App Store. Thank you. A bit longer than I thought.
Any question from the audience?
Hello, very interesting talk and many new insights. You made a statement that the cyclone which are weaker and have high central pressure are the one which are rapidly intensifying.
Potentially. Yeah.
Potentially intensifying. So what could be the probable factors that once the cyclone forms and then it has its progression over the ocean, So what makes the cyclone to drop the maximum radius of maximum winds suddenly?
So the radius of maximum wind can so there is no theory on the size, I should say that, the inner size, right? So the R max. So there's some theory on the outer size, which we published, but there are actually very few theories that fully explain what determines the size. So I don't think there is a specific answer. But what we notice very often during the rapid intensification is that rapid intensification and shrinking often coincide, but part of that is actually just a conservation of angular momentum. So you spin up because you are shrinking. Why you are shrinking, I think, is not clear at all. But so the shrinking and the spin up is actually just a conservation of angular momentum. That's part of it. There could, of course, also be the physics bit, which is causing an outflow. So that could be more enhanced convection, and you basically have more mass in this framework, more mass leaving the center. And that's probably related to, that is almost certainly related to the convection scheme. But I guess I'm just saying even the internal property of the cyclone is important. So it's not just what's going on with the sky, which is the convection, for example, but what is the actual initial state of your cyclone is very important.
So you are saying that there is a more convection happens that takes the mass out of the center.
Yes.
And that makes the maximum.
That creates an outflow, a net outflow.
Oh, thank you.
Thank you, sir, for your presentation. Sir, you have divided, one is the intensification of tropical cyclone and weakening of tropical cyclone. You have given two equations. One for that intensification of tropical cyclone, that is denoted by central pressure with time variation minus 0.8. And another one is for weakening, that is plus 0.9. So just I want to know from which criteria you have followed to describe for weakening and intensification, and in the size means in terms of distance, or you have given two plots for means intensive means for tropical cyclone pressure dependency plots you have shown with 6 hour differences. So with size. So size means distance of the tropical cyclone, or in terms of
the R max. Sorry.
Radius of maximum. Okay, sir. Thank you. Sir, can you please just differentiate between the intensification and weakening in the equations?
Yes. So there's one equation. There's one equation.
And one equation is there.
Yes.
0.8 and 0.9. Yes, you have shown. Yes, sir.
I will explain it. There is one equation.
Okay, sir.
This is the equation.
Okay, sir.
So when I said 0.8 or 0.9, this is just arguing about what is this value, right? There's one equation. So to get this equation is purely empirical. So I just fit this 99th percentile to get the slope. It's just the empirical slope. But basically, it's the same equation. It's this chi at 99th percentile. So, I mean, they could be the same. I mean, I don't know. But within the error, this could be 0.8, this could be 0.9.
Okay, it's clear. Thank you, sir.
So in this theory, it doesn't matter. The cyclone is, it's a cylinder. You just tell me how much is going in or out. But it seems it's actually from the data, it's actually a very similar number, the outflow and inflow for the weakening maximum. For the inflow and the outflow, it's remarkably the same number. In fact, in the main, here you got the outflow for the different time steps. They're actually, I mean, they're different sign, obviously, but they're actually quite similar numbers. It's quite surprising to me, because the physics should be different, or I don't know. But anyway, the rates of whether the mass goes in or out are actually similar.
Thank you, sir.
I guess that reflects the pressure tendencies are similar.
This paper which you are referring in CMW.
Which one?
22, last but one slide. Yeah.
Yeah.
So how many cases they have? Just for
I should know.
one season or something?
No. It's multi-season. I think 25 or something like this. I think 25 from memory.
25 cases?
Yeah.
I see.
So it's quite comprehensive.
What is the difference between V4 and V5? Any idea? No.
I don't know.
You
That's their problem.
Yeah. Coming back to your monsoon mission question, see, right from the time of monarchs, wherever southern monarchs or winter monarchs, whatever. So these depressions are fundamentally, structurally different than tropical cyclone, because the depressions are also most of the time the cold core structure, whereas tropical cyclone, what we normally form during pre-monsoon, post-monsoon, are warm core, and due to the monsoonal upwelling, the SSTs, etc., Arabian Sea, etc., and also the position of ITCZ. So it doesn't give any cyclogenesis, right? And also, if you see the structure as you are describing, the cyclones are always barotropic, okay, whereas depressions, they baroclinic, they have a tilt always. So there are many fundamental differences that written in the books and many literatures. So, and another thing in the recent past, what we are finding, for example, this year, there are plenty of rain, but so far no depressions. The majority of rains, it is established. It is contributed by low pressure systems, which doesn't qualify from the wind speed angle as even depressions. Okay, but they carry a lot of moisture and they give a lot of rain. Actually, low pressures are more useful than depression or cyclone in terms of widespread rainfall. So the point is that depressions. It's not that tropical cyclone was not there in monsoon mission. I think there were few projects in tropical cyclone, but because the IMD's current status is, as you said rightly, the intensity is one of the major issue, but not the tracks and the landfall is somewhat it is only for NCUM, but other models also show a relatively better skill in tracks, genesis, and landfall are much better. But and intensification also, mostly it is rapid intensification. I don't know whether they have considered that.
No, this is all cases, so it's even worse for
so what is happening in the last few years, we are finding, including ECMWF, rapid intensification and rapid weakening. Both are wrongly captured by model.
Yeah.
That is one of the issue that monsoon mission definitely can take up. There is no rule like that. Monsoon mission cannot look into cyclone. It will only look into, although the name says monsoon, right? But of course, there are projects under monsoon mission which looks into air quality forecasting, throughout the year. So just to clarify.
Yeah. But I think there was a paper by, I think it was Andy Turner from Reading, where they did a reanalysis of many monsoon depressions, and they were warm. They were warm core. I don't know. He looked at 1,000 or something, a huge number, and they were warm. And he actually shows, if you do the composite, I'm sorry, it's a weak tropical cyclone. Very weak.
Kiran Hunt also was there in that paper.
Warm and
the point is, they must have so this Andrew and his group,
Yeah. There was a reanalysis, I think, right? I can't remember. His era. And it was a huge number, very systematic, warm. And it looked cyclone. It looked like
the observation doesn't suggest that. If you go back to Monet.
But is that thousands of, he looked at thousands of depressions. It was a large number he looked at. So I think this is still open question whether they are just weak. Obviously, they are very weak. I'm not saying that. But I don't know. I think that I don't know. I think it's still a question about the baroclinic. I don't know. I don't know. And of course, not all the rain is caused by monsoon depression, so that's another debate, obviously. But I think there is some synergy and interest about, for example, the onset and the withdrawal. I mean, how that interacts. So I think, anyway, I think it's an interesting topic. I will campaign. That paper later, maybe, on this paper.
Any other question? So just one question regarding the intensity changes. At the time of landfall, actually means in Indian Ocean, mostly the cyclone decays because of landfall, mostly because the basin is very small, so it intensifies, and when it lands, it decays. So the intensity changes during the landfall is a decaying cyclone. Then the other factors are there which are not considered in this tendency calculation. No, the land friction and.
Well, they are, because I'm hiding it. Like I said, all the physics.
Oh, that
I'm hiding
that
here
component. It includes
everything. But I'm just saying, if you know this very well, you cannot escape this. So yeah, all the details of why the mass is going in or out is in this number. Because in the end, if you're the pressure, the only way you can increase the pressure at landfall is you need to put mass into this point. And this is the rate at which you're doing that. Why you do that and how you do that, I'm not telling you. I'm just saying this is the rate. You somehow have to achieve it.
Okay.
Through the friction, through the shear, whatever you want to do, it doesn't matter. In the end, it's just one number, the rate. I'm saying even if you know that rate perfectly, if you want to know the tendency, you cannot escape the geometry, the size. So whether it's expanding, for example, if the cyclone was to expand, that means for a given rate, you achieve less increase in pressure. So you need to work harder to maintain the filling, the post-landfall increase. If the size is expanding all the time, you need to put more and more. The rate at which you need to put the mass in is very hard. If it's quite small, and you put the mass in, it's dead very quickly. And it's just reflecting the simple geometry effects. So, but the details, the friction, the shear, this is hiding in this. So I'm not saying anything about the mechanism. I'm simply talking about the geometry, I guess.
Yeah, got it. Yeah. So if there are no any questions, you have questions.
Oh, more questions.
Surface side. In the vertical direction, there are turbulences and other effects actually due to convection within the cyclonic region. So we'll have impact on this, because I think there can be some factors maybe coming when you try to do for the cyclone means pressure tendency. Will not be some turbulences and other factors will also come into the picture?
So I think the answer is the same. You can invoke turbulence, you can invoke surface friction, you can invoke convection. All the physics we love and spend all our days doing. But in the end of the day, if you have a pressure reading, you need to change the mass in the column. There is no magic here. How you change the mass is, your particular flavor of interest. Could be convection, could be turbulence, could be friction, wind shear, and many, many different mechanisms. And I'm saying this is in this factor, because it's the column. So I'm integrating everything that's going on in my, and I'm hiding all the physics in here. I'm saying if you calculate this perfectly, you still cannot escape the geometry. It depends how big or small it is. So I think it's the same answer. Sorry? Assuming that I have some idea of what I'm trying to fill. So if I'm filling a cyclone, I'm now using R max here because I have observations for R max. But you could take the radius anywhere you want and say, okay, I have a depression. I want to do this radius, or I have a smaller radius. You're going to have some space where you want to increase the pressure or volume. Yes, Absolutely, but this is integrated in height, right? So this is the integral for the whole column, because the pressure is the mass of the whole column. So even when I have a surface pressure measurement, I have no idea what's going on. Is it going above, below? I have no idea. This is the mass, total mass. And so I'm saying the total mass depends on the total mass in or out. It's conservation of mass. So it's not, there's no mystery. But I think the insight of the inverse dependence of R is maybe trivial. Well, no, the derivation is trivial, but it's explicit. There's no, that's what it has to be.
Yeah, so if there are no more questions, let us thank Professor Ralf Toumi for today's very interesting talk. And he will be available for today and then tomorrow morning. If anyone want to have a discussion with you, I think he'll be happy to discuss upon.
Thank you.